whispers of the watery world. Beneath the surface, where the light softens and the world slows, there is a quiet current, a gentle, ceaseless movement that whispers secrets to the riverbed. It is a world of muted greens and browns, of shifting shadows and the slow dance of submerged plants. Here, time itself seems to stretch and unfurl, like a long silken ribbon drifting in the water. There is no rush here, no urgency, only the steady, patient rhythm of the water's embrace. Within this tranquil realm, a remarkable creature, the caddisfly larva, emerges as a central figure. This tiny builder, a delicate architect of the underwater world, embodies a quiet ingenuity and a profound connection to its environment. Its existence unveils a fascinating duality, the delicate, almost ethereal beauty of its form and habitat, contrasted with the robust, highly adapted biological mechanisms that enable its survival and intricate creations. This report delves into the hidden marvels of the caddisfly larva, exploring its unique adaptations, the artistry of its case building, and its significant role within the aquatic ecosystem. Chapter 1: The Unseen Current, a World Unveiled. The underwater realm inhabited by the caddisfly larva is one of serene beauty, characterized by muted greens and browns, shifting shadows, and the slow dance of submerged plants. In this environment, time itself appears to stretch and unfurl, inviting a contemplative pace. The caddisfly, belonging to the order Trichoptera, which means hairy wings, represents an incredibly diverse and widespread group of insects with thousands of known species across the globe. These insects are found in nearly every type of freshwater habitat imaginable, from pristine, icy mountain streams to the still, warm waters of urban waterways. The aquatic larvae are found in a vast array of habitats, including streams, rivers, lakes, ponds, spring seeps, and even temporary vernal pools. There is even a marine species whose larvae inhabit the intertidal zones of New Zealand and southern Australia, and a terrestrial European species that lives in damp leaf litter on the forest floor. The order Trichoptera boasts a wide array of species, each uniquely adapted to specific environmental parameters. These parameters include water temperature, the speed of the current, mineral concentrations, levels of pollutants, and even the amount of sunlight exposure. This high degree of specialization allows multiple caddisfly species to coexist within a single stream or river, a phenomenon known as niche partitioning. By occupying distinct microhabitats and having different tolerances, they minimize direct competition for resources. This intricate web of adaptation means that caddisfly assemblages, particularly when species rich, are excellent bioindicators of water quality. The presence, absence, or relative abundance of particular species can provide a nuanced assessment of an aquatic ecosystem's health. A key adaptation for caddisfly larvae is their ability to tolerate low oxygen concentrations, a crucial feature for survival across their varied aquatic environments. While many are found in clean, oxygen-rich waters, their capacity to endure less than ideal oxygen levels sets them apart from other aquatic insects like mayflies and stoneflies. The larval form of the caddisfly has a soft, segmented body, reminiscent of a caterpillar, which is inherently vulnerable to the abrasive nature of the substrate and the constant threat of predators. Anatomically, the larva is characterized by a hardened or sclerotized head and at least one thoracic segment, providing some protection to the front part of its body. It possesses well-developed segmented legs on its thorax and a pair of hooked prolegs at the tip of its abdomen. The abdomen itself remains soft and pale. A notable feature of the larval stage is the absence of wing pads or visible antennae. The widespread distribution of caddisflies and their species-specific adaptations to varied aquatic conditions, encompassing factors like temperature, flow, oxygen, and pollutants, reveal a sophisticated evolutionary strategy. This strategy is not merely about general adaptability, but points to a refined approach of niche partitioning. By specializing in distinct microhabitats and environmental tolerances, different caddisfly species effectively reduce direct competition. This allows for a greater overall biodiversity within a single ecosystem, explaining why they are abundant across diverse natural aquatic environments. This specialized adaptability has profound implications, making caddisflies invaluable as bioindicators of water quality. The presence, absence, or relative abundance of particular caddisfly species can provide a highly nuanced and precise assessment of environmental health, offering insights far beyond what a general classification might convey. Their capacity to inhabit a wide range of aquatic environments demonstrates a robust ecological success story, illustrating how collective specialization can lead to broad ecological penetration and sustained presence. Chapter 3: The Unseen Current, a World Unveiled. The underwater realm inhabited by the caddisfly larva is one of serene beauty, characterized by muted greens and browns, shifting shadows, and the slow dance of submerged plants. In this environment, time itself appears to stretch and unfurl, inviting a contemplative pace. The caddisfly, belonging to the order Trichoptera, which means hairy wings, represents an incredibly diverse and widespread group of insects, with thousands of known species across the globe. These insects are found in nearly every type of freshwater habitat imaginable, from pristine, icy mountain streams to the still, warm waters of urban waterways. The aquatic larvae are found in a vast array of habitats, including streams, rivers, lakes, ponds, spring seeps, and even temporary vernal pools. There is even a marine species whose larvae inhabit the intertidal zones of New Zealand and southern Australia, and a terrestrial European species that lives in damp leaf litter on the forest floor. The order Trichoptera boasts a wide array of species, each uniquely adapted to specific environmental parameters. These parameters include water temperature, the speed of the current, mineral concentrations, levels of pollutants, and even the amount of sunlight exposure. This high degree of specialization allows multiple caddisfly species to coexist within a single stream or river, a phenomenon known as niche partitioning. By occupying distinct microhabitats and having different tolerances, they minimize direct competition for resources. This intricate web of adaptation means that caddisfly assemblages, particularly when species rich, are excellent bioindicators of water quality. The presence, absence, or relative abundance of particular species can provide a nuanced assessment of an aquatic ecosystem's health. A key adaptation for caddisfly larvae is their ability to tolerate low oxygen concentrations, a crucial feature for survival across their varied aquatic environments. While many are found in clean, oxygen-rich waters, their capacity to endure less than ideal oxygen levels sets them apart from other aquatic insects like mayflies and stoneflies. The larval form of the caddisfly has a soft, segmented body, reminiscent of a caterpillar, which is inherently vulnerable to the abrasive nature of the substrate and the constant threat of predators. Anatomically, the larva is characterized by a hardened or sclerotized head and at least one thoracic segment, providing some protection to the front part of its body. It possesses well developed segmented legs on its thorax and a pair of hooked prolegs at the tip of its abdomen. The abdomen itself remains soft and pale. A notable feature of the larval stage is the absence of wing pads or visible antennae. The widespread distribution of caddisflies and their species specific adaptations to varied aquatic conditions, encompassing factors like temperature, flow, oxygen, and pollutants, reveal a sophisticated evolutionary strategy. This strategy is not merely about general adaptability, but points to a refined approach of niche partitioning. By specializing in distinct microhabitats and environmental tolerances, different caddisfly species effectively reduce direct competition. This allows for a greater overall biodiversity within a single ecosystem, explaining why they are abundant across diverse natural aquatic environments. This specialized adaptability has profound implications, making caddisflies invaluable as bioindicators of water quality. The presence, absence, or relative abundance of particular caddisfly species can provide a highly nuanced and precise assessment of environmental health, offering insights far beyond what a general classification might convey. Their capacity to inhabit a wide range of aquatic environments demonstrates a robust ecological success story, illustrating how collective specialization can lead to broad ecological success story. Chapter 2: The Gifts of the Riverbed, Nature's Palette. The riverbed, a vast and silent tapestry, truly functions as a treasure trove for the caddisfly larva, presenting a mosaic of tiny stones, grains of sand, and fragments of forgotten shells. Each piece, in its own quiet way, holds a unique story, offering itself as a potential building block for the larva's protective sanctuary. The caddisfly larvae utilize an extensive array of natural materials for constructing their cases. These include fine sand grains, larger fragments of rock, bits of bark, small sticks, various leaves, seeds, mollusk shells, and other forms of detritus found in their immediate surroundings. A fascinating aspect of this construction is that the specific choice of materials and the overall design of the case are often genetically determined and species specific, serving as distinct identifiers that can help classify caddisfly larvae down to their family or even genus level. In a striking example of this specificity, some species are known to incorporate unusual items like mollusk shells into their cases, while others use various pieces of plant material, and some use only leaf fragments. The type of case a caddisfly larva constructs is often a direct reflection of its preferred habitat and feeding strategy. For instance, species found in the slow-moving waters of shallow lakes and ponds typically build cases from organic matter like vegetation and debris. These cases are often neutrally buoyant, preventing them from being swept away in gentle currents where such debris naturally accumulates. In contrast, caddisflies inhabiting soft sediment environments construct wide, flattened cases that function much like snowshoes, distributing their weight and preventing the insect from sinking into the soft substrate. For areas with faster currents, larvae create heavier cases using sand and rocks, which provide the necessary ballast to resist dislodgement by strong water flow. Some species demonstrate a remarkable ability to adjust their building materials based on the current speed. The faster the flow, the larger the stones they incorporate into their cases. Beyond these portable cases, some species, particularly those in the Anulopalpia suborder, adopt a different strategy, building fixed retreats anchored to rocks. These stationary shelters support a distinct feeding method where the larva remains in place, often spinning silken nets to capture food particles from the water column. This contrasts with the Integrapalpia suborder, whose larvae construct portable cases that allow them to move around while foraging. There are also free-living caddisflies that do not build cases until they are ready to pupate. The behavior involved in making these constructions is closely related to the cocoon building of their terrestrial relatives, moths and butterflies. The precise correlation between the case's material and design and the specific habitat conditions reveals a sophisticated level of biomechanical engineering and resource optimization within caddisfly larvae. This goes far beyond simple shelter building. The case is not merely a static shield, but a dynamic, multifunctional tool. The selection of materials is not arbitrary. It represents a direct, optimized response to specific physical forces and environmental challenges. For example, the choice of lighter organic materials in slow water aids buoyancy, while heavy sand and rock cases in fast currents provide essential weight. The flattened cases function to distribute weight over soft sediment, preventing sinking. This demonstrates an innate understanding of physics and material science, allowing the larva to instinctively engineer its survival and mobility within its ecological niche. This level of precise inherited engineering, where case design is genetically determined, underscores the immense power of natural selection in shaping complex behaviors and structures. It transforms the gifts of the riverbed from mere raw materials into a tailored toolkit that the larva instinctively knows how to utilize for optimal survival, showcasing nature's profound efficiency. Chapter 4: The Delicate Selection, Instinct and Precision. The act of selecting materials for its case is a quiet ballet, a dance of intuition and precision performed by the tiny caddisfly larva. It is not a hurried choice, but a delicate discernment, a gentle sifting through the countless offerings of the riverbed. Each potential building block is approached with a profound sense of calm, a quiet reverence for its unique qualities. The larva employs its tiny, very short antennae, which function like delicate wands, sweeping gently across the surface of a pebble. These antennae are exquisitely sensitive, capable of detecting the most subtle vibrations and minute shifts in the water's flow around an object. This is how the larva perceives its world, not primarily with eyes, but through a profound sense of touch and a deep connection to the physical sensations of its environment. The cool smoothness of a water-worn stone, the rough texture of a newly broken fragment, the subtle grit of a cluster of sand grains, each sensation contributes a piece of information, guiding its quiet decision. Following this initial tactile exploration, the larva's delicate and precise mouth parts, which are designed for chewing, come into play. These are not for aggressive biting, but for gentle manipulation, for testing the weight and stability of each piece. The larva might gently prod a stone, feeling its resistance and firmness, or lift a grain of sand, assessing its lightness and perfect roundness. This is a slow, meditative process, a tactile investigation that allows the larva to truly understand the essence of each material. There is no rush, no urgency, only the quiet unfolding of this sensory examination. The larva possesses an innate knowing, an ancient wisdom that guides its choices. While much of this behavior is believed to be fixed, some studies have shown a degree of flexibility. For instance, when deprived of their natural building materials, like leaves, caddisfly larvae have been observed to use unnatural materials like paper to rebuild their cases, though they show a clear preference for natural materials when given a choice. It does not consciously weigh options or calculate angles. Instead, it feels, senses, and understands the subtle language of the stones and sand. It discerns which piece will fit perfectly into the emerging structure, which texture will provide the best grip, and which shape will contribute to the overall strength and harmony of its growing home. This knowledge is not learned but inherent, a quiet hum within its tiny being, serving as a silent compass guiding its every delicate movement. The caddisfly larva's response to light, known as phototaxis, presents a complex and seemingly contradictory picture, highlighting a highly context dependent and adaptive behavioral plasticity. Some research indicates that caddisfly larvae may drift in the water column around midday, which might suggest a tolerance or even attraction to light during certain periods. This behavior could be linked to specific daytime activities, such as case building, where improved visibility could be advantageous, or for finding suitable attachment points. Conversely, many adult caddisflies are nocturnal and strongly attracted to light, a common behavior among moth like insects. This attraction to light in adults is often associated with mating or dispersal. The larval response to light may be different, with some studies suggesting they are repelled by light to avoid predators. However, the pupation process is influenced by factors including light exposure, suggesting a shift in their response. The complex and seemingly contradictory phototaxis behavior of caddisfly larvae is not indicative of a flaw in research, but rather demonstrates a highly adaptive behavioral plasticity. This reflects different survival priorities at different times or life stages. The caddisfly larva's response to light is not a fixed singular reaction, but a dynamic adaptive behavior that likely shifts based on several factors. Its life stage, for instance, dictates different needs compared to an adult caddisfly. The immediate behavioral goal also plays a crucial role, seeking light for construction or finding attachment points during the day optimizes building conditions, while seeking darkness at night or during vulnerable periods, like feeding or avoiding predators, is a defensive strategy. The quality and intensity of light also matter, avoiding harsh direct light, which carries risks, while perhaps being drawn to ambient diffused light, could be part of this nuanced response. Finally, a late stage shift to photoneutral or even photopositive behavior could be a specific trigger to facilitate emergence for pupation. This behavioral flexibility underscores the sophisticated sensory processing and decision making capabilities present even in tiny invertebrates. It illustrates how organisms can fine tune their responses to environmental cues to optimize survival across various activities and life stages, showcasing a deeper level of biological intelligence and adaptation within the delicate selection process. Chapter 5: The Invisible Thread, Engineering Marvel. Once a piece of material is chosen, a tiny invisible thread comes into play. This is the silk spun by the caddisfly larva itself, a marvel of natural engineering. It is not a loud or visible material, but a soft, translucent filament, strong yet gentle, capable of binding the disparate elements of the riverbed into a cohesive, protective whole. This silk emerges from the larva's tiny body, appearing as a delicate, shimmering strand in the clear water. Though almost imperceptible, it possesses an incredible strength and a quiet tenacity, allowing it to hold fast against the gentle tug of the current. This silk embodies the very essence of connection, serving as the invisible bond that transforms individual fragments into a unified structure. It stands as a testament to the hidden wonders of the natural world, where remarkable strength can be found in the most delicate of forms. The evolutionary development of this silk production is a key adaptation that has contributed to the caddisfly's success and diversification. The larva uses this silk with exquisite precision. Its application is not hurried, but involves slow, methodical weaving and gentle attachment of each chosen piece. The silk is produced by modified salivary glands, known as labial glands, and extruded through an organ called a spinneret, located near the mouth. This is similar to their terrestrial relatives, the Lepidoptera, moths, and butterflies. The silk is applied in tiny, deliberate movements, wrapping around the edges of a pebble, adhering to the surface of a grain of sand, and securing a fragment of shell. Each application represents a quiet act of commitment, a small step forward in the creation of its sanctuary. The water flows around the larva as it spins its silk, acting as a constant supportive presence. The current subtly assists, guiding the silk into place and ensuring a smooth and even application. This represents a partnership between the tiny builder and the vast flowing river, a silent agreement of purpose and support. The water does not interfere, but rather facilitates the larva's intricate work. The silk functions as a soft, invisible glue, binding the rough edges of stones and smoothing the transitions between different textures. It creates a seamless surface, forming a protective layer that envelops the larva's soft body. This act of binding is a quiet meditation, a repetitive motion that deepens the larva's focus and reinforces the growing sense of security within its emerging home. The unique properties of caddisfly silk stem from its chemical composition and the process of its formation. The silk is composed of large proteins known as fibroins, specifically a heterodimer of heavy and light fibroin proteins. It exhibits viscoelastic properties, distinct yield behavior, large strain cycle hysteresis, and nearly complete recovery of its initial strength and stiffness when unloaded, making it incredibly resilient. It serves a dual function, forming both the silk thread and an underwater cement. The remarkable underwater adhesion of caddisfly silk is rooted in its sophisticated chemistry. A key difference from the silk of terrestrial insects is that the serines, an amino acid in caddisfly silk, are phosphorylated, meaning phosphate groups are added to them. These phosphate groups are negatively charged and are known to be excellent adhesion promoters, even used in some dental fixtures and water-based paints. These negatively charged phosphates interact with positively charged cations, such as calcium and magnesium, that are naturally present in the aquatic environment. These metal ions are integrated into the silk fibers directly from the water during the spinning process and are vital for the silk's solidification and rigid structure. This unique chemical makeup allows the silk to bond to a wide range of both organic and inorganic surfaces underwater. The caddisfly's silk represents a pinnacle of bio-inspired material science, demonstrating how subtle chemical modifications, such as phosphorylation and the active integration of environmental cations, can transform a common biological material like silk into a highly specialized, superior adhesive for extreme underwater environments. This sophisticated bioadhesion mechanism has significant implications beyond the caddisfly itself, offering a blueprint for developing novel, biocompatible, and water resistant adhesives and biomaterials for medical and industrial applications. There is growing interest in using caddisfly silk for purposes such as tissue engineering and as a wet band aid in surgery, given its versatility, biocompatibility, mechanical strength, and elasticity. Remarkably, obtaining caddisfly silk in industrial quantities is becoming as feasible as acquiring spider silk, opening avenues for future technological advancements. The invisible thread is thus not just a biological curiosity, but a profound source of inspiration for advanced human engineering, showcasing nature's elegant solutions to complex material challenges. Chapter 6: A Tiny, Moving Sanctuary. Form and Function. As the caddisfly larva continues its patient work, the jeweled case slowly takes shape around its soft body. It is more than just a collection of stones and sand. It is a tiny moving sanctuary, a portable home that offers protection and peace in the gentle flow of the stream. This case is a testament to the larva's ingenuity, a quiet marvel of natural design, providing a profound sense of safety within. The larva's soft body is cradled within, shielded from the gentle currents and hidden from the larger world. This deep sense of security allows the larva to rest, grow, and simply exist. The case is not a prison, but a haven, a quiet retreat where the larva can find solace and stillness. The exterior of the case is a mosaic of the riverbed itself. Each stone, grain of sand, and shell fragment, meticulously chosen and placed, creates natural camouflage, rendering the larva almost invisible to casual observers. This quiet blending with its surroundings provides an additional layer of protection, a silent cloak that allows the larva to move through its world undisturbed. Beyond camouflage, the case serves as a physical barrier against predators. When preparing for pupation, case-bearing species attach their portable cases to an underwater object and seal both the front and back openings, enhancing protection against predators during this vulnerable stage. The case also acts as an abrasion barrier, shielding the larva's soft body from the abrasive substrate. Furthermore, heavier cases, constructed from sand and rocks, provide essential ballast, helping the larva maintain its position in strong currents and preventing it from being swept away. A critical function of the caddisfly case relates to respiration. Portable caddisfly cases are typically open at both ends. Larvae draw oxygenated water through the posterior rear end of the case, allowing it to flow over their tracheal gills and then pump it out of the wider anterior front end. Crucially, the larva's undulating movements within the tube help to maintain this water current, which is especially important in still or slow moving water. This mechanism enables caddisfly larvae to inhabit waters with lower oxygen content, where other aquatic insects like stoneflies or mayflies might not survive. It is also important to distinguish between the main suborders of caddisflies. Integrapalpia larvae construct portable cases which allow them mobility while foraging for food. In contrast, Anolepalpia larvae create fixed retreats, remaining stationary and waiting for food to come to them, whether as filter feeders or as carnivores rushing out to attack prey. The caddisfly case exemplifies sophisticated biomimicry and multifunctional design, where a single structure simultaneously addresses challenges of defense, mobility, and vital physiological processes like respiration through elegant, integrated solutions. The case is a masterclass in integrated design. Its form, such as being tubular and open ended, and its material composition, chosen directly from the environment, are not isolated features. Instead, they are intricately linked to support multiple, often interdependent survival functions. For example, while the open ends are necessary for respiration, this design choice is compensated for by the larva's internal movement, which actively maintains the water flow. This ensures both robust protection and physiological viability, allowing the caddisfly to thrive even in low oxygen environments. Similarly, the material choice, such as using heavy stones in fast currents, directly impacts its function as ballast and mobility, while simultaneously providing effective camouflage. This demonstrates a holistic design approach by nature, where structures are optimized to serve numerous purposes simultaneously, often with remarkable simplicity. This multifunctional design principle is a core concept in biomimicry, illustrating how evolution creates integrated solutions that address multiple constraints and needs. This comprehensive security ultimately contributes to the enduring peace the larva experiences within its self made sanctuary. Movement, a quiet beat in the symphony of creation. This patient construction is part of a larger life cycle, as caddisflies undergo complete metamorphosis, similar to butterflies and moths, passing through several distinct stages: egg, larval, pupal, and adult. The life cycle begins when adult females lay their eggs, with a single female capable of laying a large number of eggs. These are often laid in or near water, with the female sometimes walking or diving into the water to cement the gelatinous egg mass to aquatic vegetation or stones. The presence of moisture is essential and triggers the eggs to hatch, which can take from a few days to a few weeks. Upon hatching, caddisfly larvae typically go through several stages of development, known as instars, with each stage punctuated by a molt. The first instar may remain within the protective gelatinous matrix for a period before venturing out to begin constructing its case or spinning a silk net. The larval stage is the longest part of the caddisfly's life, often lasting for a year or more. A remarkable aspect of their larval stage is their ability to overwinter. Most caddisfly larvae spend the winter in their larval form, with very little growth occurring during this time. They can endure being embedded in ice for months, tolerating freezing temperatures. Some species, however, have different strategies, overwintering as eggs protected within the gelatinous matrix. This extended larval period, particularly the final instar, is a time of significant feeding to store energy for the upcoming transformation. Following the larval stage, the final instar seals its case underwater, attaching it to a solid object, and enters a stiff prepepal resting stage before pupating inside. The pupal stage typically lasts for a few weeks, though some species may overwinter as pupae. When the pupa has fully developed into an adult and is ready to emerge, it uses specialized mandibles to chew its way out of the case and swim to the water's surface. The adult caddisflies are terrestrial, moth like insects, often active at night and seeking cool, moist habitats like riparian vegetation during the day. With reduced mouth parts, most adult caddisflies do not feed, or they may sip nectar. Their brief adult life is primarily focused on reproduction. Most caddisfly species complete this entire life cycle within approximately a year's time, though larger species in colder climates may require more time to develop fully. The larva's profound patience is evident throughout this process as it focuses on the next piece, the next attachment, the next small step. This unwavering focus and deep immersion in the present moment are sources of profound peace, demonstrating the power of breaking down a large task into tiny, manageable actions, each performed with quiet dedication. The building of its case is an intrinsic part of its being, a natural expression of its purpose. The caddisfly's life cycle, particularly its extended larval and overwintering stages, reveals a strategy of temporal resource allocation and resilience. In this approach, slow, patient development is prioritized over rapid growth, enhancing survival in fluctuating aquatic environments. The long larval stage and overwintering are not merely passive survival mechanisms, but represent an active strategy of temporal resource management. By delaying development during unfavorable conditions, such as extreme cold, low nutrient availability, or being encased in ice, the caddisfly conserves energy and avoids periods of resource scarcity. This ensures that growth and metamorphosis occur when environmental conditions are optimal. This unhurried pace is a highly adaptive mechanism for surviving seasonal environmental fluctuations. This resilience in challenging environments often stems from patience and the ability to pause and wait for the right conditions rather than continuous rapid growth. This understanding reinforces the report's theme of an enduring peace found in nature's patient unfolding, extending beyond just the physical act of building to encompass the entire rhythm of its existence. Chapter 8: The Enduring Peace, Ecological Significance and Beyond. Finally, the jeweled case is complete. A tiny masterpiece, crafted from the very essence of the riverbed, stands as a testament to the caddisfly larva's unwavering patience and quiet artistry. It is a perfect miniature home, a protective shell that reflects the muted beauty of its underwater world. Within its walls, the larva rests, enveloped in a profound and enduring peace. This finished case drifts gently with the current, its meticulously chosen and seamlessly bound stones, sand grains, and shell fragments shimmering softly in the diffused light. It is a quiet jewel, a natural sculpture that speaks of harmony and stillness, a tiny, self contained world in gentle motion. The larva, nestled deep within its sanctuary, experiences the comforting embrace of its creation, with the cool water flowing around its exterior as a soft, non intrusive caress. The sounds of the stream are muffled and distant, a gentle hum that lulls the larva into deep contentment. With its purpose fulfilled, there is no further need for building or searching, only the quiet satisfaction of a task completed. This enduring peace is not a fleeting moment, but a continuous state of being, as the case provides constant protection and a reliable haven from the gentle forces of the stream. The larva is safe, secure, and utterly at rest, allowing its tiny body to relax completely and surrender to the quiet rhythms of its existence. This state is a profound stillness, a deep restorative calm that permeates its entire being. The journey of this tiny creature, from a soft, vulnerable larva to a master builder of its own protective home, is a journey of quiet transformation. It stands as a testament to the innate wisdom that guides life in its simplest forms. The case is more than just a shelter. It symbolizes resilience and the ability to create one's own sanctuary from the elements of the world. This quiet strength and gentle self reliance are profound sources of peace. Beyond its individual existence, the caddisfly holds significant ecological importance, particularly as a bioindicator of water quality. It is recognized as one of the most commonly used insect orders for assessing aquatic ecosystem health, alongside mayflies and stoneflies. Most caddisfly species are intolerant of pollution, meaning their diminished numbers in a habitat can signal environmental degradation. Conversely, some species are less sensitive or may even thrive in slightly polluted conditions with elevated nutrient levels, often due to an increase in their favored food, paraphyton. This nuanced response provides a more comprehensive picture of water quality. Their case making behaviors, linked to their environmental roles and respiratory efficiency, further enhance their reliability as pollution indicators. Caddisflies also play a vital role in the aquatic food web, serving as a crucial food source for a wide range of aquatic and terrestrial predators. They are a major component in the diet of many fish, especially trout and other bottom feeding freshwater fish. The newly emerged adult is particularly vulnerable and an easy target for fish. Aquatic birds, some mammals, amphibians, reptiles, spiders, and dragonflies also feed on caddisflies. Furthermore, case-making caddisflies contribute to the cleaning of their aquatic environment and to nutrient cycling. By cutting up vegetation for case construction, and through their diverse feeding habits, which include shredding plant debris, scraping algae, and collecting organic particles, they help break down organic materials, making nutrients available to other organisms. Their case building activities can even help stabilize gravel beds, preventing sediment erosion. In terms of human interaction, caddisfly cases have found unique applications, such as being incorporated into distinctive jewelry. They are also utilized in forensic entomology. While largely beneficial, there are minor negative impacts, such as occasional damage to rice crops or causing allergic reactions in some individuals. Anglers also recognize their importance, using lures that mimic caddisfly larvae and adults. The caddisfly's multifaceted ecological roles, from a precise bioindicator to a keystone food source and an active environmental cleaner, underscore its position as a critical nexus in aquatic ecosystem health. Its seemingly simple existence has profound ripple effects throughout the food web and significantly impacts environmental quality. As bioindicators, their presence or absence directly reflects water quality, which in turn influences the health of the entire food web, for which caddisflies are a major food source. Their feeding and case building activities actively process organic matter, influencing nutrient cycling and water clarity, which further impacts the ecosystem's overall health. This creates a feedback loop where the caddisfly's well being is both a result of a healthy environment and a contributor to its maintenance. The enduring peace of the caddisfly's existence is intrinsically linked to the enduring peace of its ecosystem. Its quiet work and presence are fundamental to the stability and productivity of freshwater habitats. This highlights the profound interconnectedness of all life and the significant impact even the smallest creatures can have on the grander scheme of nature, urging a deeper appreciation for the subtle yet critical roles played by seemingly insignificant organisms. Conclusion: the vast, intricate tapestry of the natural world is woven with threads of quiet ingenuity, with countless organisms demonstrating profound solutions to the fundamental challenges of existence. Among these, the humble caddisfly larva stands as a paragon of natural resilience, a master artisan whose life is a testament to the power of intricate adaptation and the quiet beauty inherent in biological processes. Its remarkable journey from a vulnerable, soft bodied creature to the architect and inhabitant of a self made, often jeweled sanctuary offers a deep and compelling narrative of survival, instinct, and meticulous creation. This tiny architect, navigating its complex watery world, showcases an astonishing repertoire of behaviors and biological tools from its species specific adaptations to a wide array of aquatic habitats and its nuanced responses to subtle environmental cues, to the astonishing bioengineering of its underwater silk and the multifunctional brilliance of its portable home, the caddisfly larva is a subject of endless fascination. To delve into its world is to witness a master class in natural engineering, a slow, deliberate process of construction that speaks volumes about the enduring power of evolution and the unhurried rhythm of life itself. The story of the caddisfly larva is at its core a story about vulnerability overcome by innovation. Born as a soft, fleshy grub, it is a tempting and easy meal for a host of predators that patrol the stream beds, from dragonfly nymphs and stoneflies to the ever watchful trout. In the ceaseless, often turbulent flow of rivers and streams, its delicate body is susceptible to abrasion, to being swept away into unfavorable environments, or to being crushed by shifting substrates. This inherent fragility is the evolutionary crucible in which its most famous trait was forged, the creation of a protective case. This is not a mere shelter, but a masterpiece of functional design, a tailored suit of armor, a ballast against the current, and a perfectly camouflaged redoubt from which to forage. The sheer variety of these cases across the more than 14,000 species of caddisflies worldwide is a breathtaking illustration of adaptive radiation. Each design is a unique answer to a specific set of environmental questions posed by the larva's habitat. Some, living in the swift currents of mountain streams, construct heavy streamlined cases from grains of sand and tiny pebbles glued together with a silken mortar that is itself a marvel of biochemical engineering. These dense, robust structures act as anchors, preventing the larva from being washed downstream and providing formidable protection against predation. The smooth, rounded surfaces reduce hydraulic drag, allowing the larva to navigate the powerful forces of its environment with an elegance that belies its simple form. In stark contrast, caddisfly larvae that inhabit the calmer, detritus rich waters of ponds, lakes, and slow moving rivers often adopt a different architectural philosophy. Here, the primary challenges are not the force of the current, but rather concealment and buoyancy. Species in these environments often construct their cases from lighter organic materials, fragments of leaves, hollow reeds, small twigs, and even the discarded shells of tiny snails. These cases are masterpieces of camouflage, rendering the larva virtually invisible against the cluttered floor of the pond or stream. The use of buoyant materials can also aid in mobility, allowing the larva to move with greater ease through the water column or across mats of aquatic vegetation. The deliberate, almost artistic arrangement of these materials is a sight to behold. A larva might cut a perfect square from a fallen leaf to form the foundation of its home, or arrange twigs in a spiral or log cabin formation, creating structures of surprising complexity and geometric precision. This selection is not random. It is a highly evolved instinctual behavior. The larva uses its mouth parts and legs to meticulously examine potential building materials, testing them for size, shape, and weight, before carefully manipulating them into position and binding them with silk. This process, a slow and deliberate ballet of construction, can take hours or even days, a testament to the unhurried yet persistent rhythm of the natural world. The true genius of the caddisfly larva's creative process lies in its silk. Produced by specialized salivary glands, this adhesive substance is a complex cocktail of proteins that polymerizes almost instantly upon contact with water. Unlike the silk of a spider or a silkworm, which is spun in the air, caddisfly silk is an underwater adhesive, a form of natural cement that has captivated and inspired scientists for decades. Its properties are extraordinary. It is both incredibly strong and remarkably flexible, capable of binding together materials as disparate as smooth grains of sand, rough pieces of bark, and the sharp edges of rock fragments. It maintains its adhesive power in a wide range of water temperatures and chemical conditions, a feat that human engineers have struggled to replicate. Researchers studying this remarkable biopolymer have identified key proteins called phosphoproteins that are rich in the amino acid serine. These serine residues are phosphorylated, meaning they have phosphate groups attached, which are believed to play a crucial role in the silk's ability to bond so effectively underwater by displacing water molecules from the surfaces of the materials being joined. This underwater glue is the silent, indispensable partner in the larva's architectural endeavors, the thread that literally holds its world together. The energy and resources required to produce this silk are significant, underscoring its vital importance to the larva's survival. Beyond the sheer diversity of materials and forms, the architecture of the caddisfly case is a sublime example of multifunctional design. It is first and foremost a shield. When threatened, the larva can retract its vulnerable head and legs completely into the case, leaving only the hard, unappetizing exterior exposed to a potential predator. The case's texture and composition provide excellent camouflage, breaking up the larva's outline and allowing it to blend seamlessly into its surroundings. But its function extends far beyond passive defense. The case is also a respiratory aid. By undulating its body within the tube, the larva creates a current of water that flows over the gills located along its abdomen. This ensures a constant supply of oxygen, even when the surrounding water is relatively still. The case, therefore, is not just a home, but also a lung, a personalized life support system that allows the larva to thrive in a variety of oxygen conditions. Furthermore, the case serves as a critical tool for feeding. The larva can extend its head and thoracic legs from the opening of the case to graze on algae and detritus from surrounding surfaces, much like a tortoise emerging from its shell. The weight and stability of its home allow it to maintain its position while foraging, even in moving water. For net spinning caddisflies, which do not build portable cases, This same silk is used to construct intricate nets, often positioned in the current to catch drifting organic particles and smaller invertebrates. These nets are marvels of hydrodynamic engineering, shaped and oriented to maximize capture efficiency while minimizing the risk of damage from the flow. The life of the caddisfly larva, encapsulated within its self made world, is a continuous demonstration of patience and the power of focused, incremental effort. In a world that often celebrates speed and explosive progress, the larva offers a different model, that of slow, deliberate, and meticulous creation. The selection of each grain of sand, each fragment of leaf, is a considered act. The spinning of each thread of silk is a precise and practiced motion. This unhurried rhythm mirrors the gentle pulse of the underwater ecosystem it inhabits, a world governed by the slow cycles of growth and decay, of deposition and erosion. This quiet persistence culminates in a state of profound and enduring security, a tranquility found within the sanctuary of its self crafted haven. It is a peace born not of passivity, but of proactive and painstaking labor. The larva's existence is a powerful reminder that true strength and resilience often stem not from grand, singular gestures, but from the steady, focused accumulation of small, well executed efforts. It is in this patient artistry that the caddisfly larva finds its strength, transforming its initial vulnerability into a state of fortified grace, a living sculpture moving through the quiet depths. This journey, from a naked and exposed grub to the master of a jeweled and functional fortress, is one of the most compelling and instructive narratives in all of nature, a silent epic of survival and a profound reflection of the quiet, understated beauty of life's enduring processes. Winding down the unhurried rhythm of creation, patience, persistence, and the architecture of peace. The life of the caddisfly larva, as we have seen, is a masterwork of adaptation. Yet beyond the cold hard facts of evolutionary advantage, its existence offers a more profound, almost philosophical lesson. The larva's daily life is a continuous and resonant demonstration of patience, a living embodiment of the unhurried rhythm of creation. In a world both human and natural, often characterized by frantic haste and convulsive change, the caddisfly larva's slow, deliberate actions stand in stark, beautiful contrast. Its methodical approach, from the initial prospecting for materials to the final exquisite construction of its case, mirrors the gentle, inexorable pulse of the underwater world it inhabits. This quiet persistence, this devotion to a task performed with meticulous care, does not culminate in a frantic victory, but in a state of profound and enduring peace, a deep tranquility found only within the self crafted haven it calls home. To observe the caddisfly larva is to be reminded that true sustainable progress, whether in the building of a tiny aquatic shelter or the shaping of a life, often stems from steady, focused, and unhurried effort. Let us immerse ourselves in the sensory world of this tiny artisan and witness this process unfold. The journey begins not with a grand design, but with a fundamental instinctual drive for security. A newly hatched larva, a mere sliver of life, is acutely aware of its own fragility. The world is a cacophony of threats, the crushing weight of shifting stones, the shearing force of the current, the ever present shadow of a predator. Its first act, therefore, is an act of creation driven by necessity. It begins a patient, painstaking survey of its immediate environment, a process of exploration that is both tactile and intuitive. Using its three pairs of thoracic legs, themselves marvels of articulated sensitivity, and its delicate mouthparts, it begins to touch, to probe, to know its world. It is a quest for the perfect components, the elemental building blocks of its future sanctuary. Imagine the larva anchored to a submerged stone, extending its body to examine a nearby grain of sand. It is not a cursory glance, it is a detailed assessment. With its legs, it rotates the grain, gauging its weight, its texture, its angularity. Is it too heavy, a burden to its own mobility? Is it too light, offering insufficient ballast against the stream's relentless push? Does it have the right facets, the ideal surfaces to which its miraculous silk can bind? This is a form of embodied cognition, where thought is not an abstract process, but is enacted through physical interaction with the world. The larva does not conceptualize its home, it feels its way to a solution. It may test a dozen grains before finding one that meets its exacting instinctual criteria. It then carefully grasps its chosen piece, a tiny jewel unearthed from the riverbed, and rotates it into the precise orientation required. Then, with a motion of its head, it dabs a single viscous thread of silk, binding the grain to its nascent structure, and so it continues, one element at a time. A grain of quartz, then a fragment of feldspar, then a tiny dark fleck of mica. Each addition is a considered choice, a deliberate act in a slow, accumulative process of construction. This unhurried tempo is not a sign of lethargy or indecision, it is a hallmark of mastery. The larva works with the confident pace of a seasoned craftsman, one who understands that haste leads to weakness and that a solid foundation requires time. In faster currents, the architectural challenge is primarily one of engineering. The larva selects heavier, more angular stones, interlocking them like a master stonemason, building a dry stack wall. The final structure is often a work of hydrodynamic genius, a curved, tapering tube that presents a minimal profile to the current, allowing water to flow smoothly over it. The weight provides stability, a crucial anchor in a turbulent world. The sheer physical effort required is immense. The larva, weighing only a fraction of its building materials, must wrestle these miniature boulders into place, a tiny Sisyphus succeeding through sheer dogged persistence. It is a testament to the power of leverage and the unwavering application of force over time. In the quiet backwaters of a pond or the slow meander of a lowland stream, the creative challenge shifts from engineering to artistry, the art of camouflage. Here, the larva becomes a master of collage. Its materials are not the cold, hard minerals of the mountain brook, but the soft, organic detritus of the forest floor. It seeks out waterlogged twigs, decaying leaf fragments, the hollow stems of reeds, and even the discarded shells of aquatic snails. The goal is not to resist the current, but to disappear. It might cut a neat rectangle from a fallen oak leaf, bend it into a cylinder, and stitch the seam with silk. It might arrange a series of hollow grass stems in parallel, creating a lightweight, buoyant tube that resembles a random piece of floating debris. Perhaps most astonishing are the log cabin cases, where the larva snips twigs into uniform lengths and arranges them in a perpendicular, interlocking pattern, building a four-sided structure of remarkable geometric precision. Each piece is chosen not only for its structural properties, but for its color, its texture, its ability to blend into the dappled light and cluttered substrate of the pond floor. This is not mere assembly, it is a form of natural impressionism, a creation designed to deceive the eye and meld perfectly with its surroundings. Central to this entire creative endeavor is the larva's silk, the thread that weaves its world into being. The application of this silk is as deliberate as the selection of materials. The larva does not waste this precious, energetically expensive resource. It applies the adhesive with pinpoint accuracy, dabbing it at key stress points, reinforcing joints and smoothing seams. The head and thorax of the larva, emerging from the opening of its case, perform a delicate ballet. The legs hold a new component in place while the head dips and weaves, spinning the silken thread that will make the structure whole. This is a process of stitching, of binding, of making connections. It is a quiet, internal monologue of creation, a conversation between the organism and its environment, mediated by a thread of protein. This act of binding disparate elements, a piece of stone, a fragment of wood, a sliver of leaf, into a single coherent functional whole, is a powerful metaphor. It speaks to the interconnectedness of the ecosystem and the way in which life constructs order and stability from the raw, often chaotic materials of the world. As the structure takes shape, as the walls of its fortress rise around its soft body, a profound transformation occurs. The larva, once vulnerable and exposed, becomes secure. This is the culmination of its patient labor, the attainment of peace. This is not the passive peace of inactivity, but the earned peace of security, a tranquility born from its own diligent work. Within its custom-built sanctuary, the world is muted. The roar of the current is softened to a gentle vibration. The threat of a predator's jaws is replaced by the solid, reassuring pressure of its own walls. From this position of safety, the larva can now perform its other essential life functions with a newfound confidence. It can extend its head and graze on the biofilm of algae coating a nearby rock, its heavy case holding it steady. It can retreat into the darkness of its tube and, with rhythmic undulations of its abdomen, draw a life-giving stream of oxygenated water over its gills. The case becomes its anchor, its shield, its lung, and its larder. It is the center of its universe, a portable world that allows it to navigate the larger, more hazardous world outside. This state of enduring peace is not static. Life is growth, and as the larva grows, its home must grow with it. The process of creation is never truly finished. With each molt, as its body expands, the larva must undertake renovations. It methodically adds new material to the anterior opening of its case, extending the walls, seamlessly blending the old with the new. The transition point between the older, darker, algae-stained materials and the fresh new additions is often clearly visible, a growth ring that tells the story of the larva's life, much like the rings of a tree. This constant cyclical act of maintenance and expansion further underscores the theme of patient, persistent effort. The larva's peace is not a final destination to be reached, but a state to be continually maintained through diligent, mindful work. It is a living process, a dynamic equilibrium between the organism and its environment. In reflecting upon this unhurried rhythm, we find a powerful antidote to the modern cult of speed. The caddisfly larva reminds us that there is a profound wisdom in slowness, a strength in deliberation. It teaches that the most resilient structures, the most secure sanctuaries, are not built in a day. They are the result of countless small, well-executed actions, accumulated over time. The peace it finds within its jeweled case is a direct consequence of the patience invested in its construction. It is a peace that is woven, thread by thread, from the very fabric of its environment, a quiet harmony between creator and creation. As we contemplate this miniature world of focused effort, we may find inspiration in its gentle, persistent pace, and recognize the deep, abiding truth that the most enduring forms of peace, both for a tiny aquatic insect and for ourselves, are those we patiently build with our own hands.